In this episode, we're going to focus on how good network design can make intrusion harder, slower, and more visible, even when something inside the environment gets compromised. Beginners often picture defense as a strong outer wall that keeps attackers out, but real security design assumes some attacker activity will eventually get inside, whether through phishing, stolen credentials, or a vulnerable service. When that happens, the question becomes whether the network gives the attacker a smooth highway to move around, or whether it forces them into narrow, controlled paths where they're easier to stop. Egress control, chokepoints, and barriers to lateral movement are three ideas that shape that outcome. These ideas are not about adding a single magic tool. They are about how traffic is allowed to flow and how much freedom compromised devices have. If you learn to think in terms of restricting pathways and creating observation points, you can understand why certain environments contain incidents quickly while others get overwhelmed. Let's start with egress control, because it's one of the most misunderstood concepts in beginner security. Egress means outbound traffic, the connections and data leaving your network toward the internet or toward other external networks. Many environments focus heavily on inbound traffic, trying to block external attackers, but they allow almost any outbound connection because it seems convenient and because many legitimate services require outbound access. The problem is that attackers rely on outbound connectivity too. Malware often needs to contact external servers to receive instructions, download additional components, or send stolen data out of the environment. If outbound access is wide open, an attacker's tools can communicate freely and data exfiltration becomes easier. Egress control is the practice of limiting and monitoring outbound traffic so that only necessary destinations, ports, and protocols are allowed, and so that suspicious outbound patterns stand out. A helpful way to think about outbound restrictions is to imagine that most devices do not actually need to talk to the entire internet in arbitrary ways. A user workstation may need web access, name resolution, and access to a set of business services, but it may not need to initiate connections on unusual ports or to random external servers. A server that hosts an internal database may need even less outbound access, because its job is to serve internal clients, not to browse the web. When you align outbound permissions with real needs, you shrink the number of options an attacker has after compromise. This doesn't mean blocking everything. It means being intentional about what is allowed. The stronger the alignment between business need and allowed egress, the more you can treat unexpected outbound connections as suspicious instead of normal background noise. Chokepoints are the places where traffic is forced to pass through a narrow set of controlled devices or paths. In a well-designed environment, important outbound traffic goes through a small number of gateways, such as a secure web gateway, a proxy, or a firewall that enforces policy. The value of a chokepoint is that it concentrates decision-making and logging, which supports both prevention and detection. If every device can reach the internet directly through many uncontrolled paths, you lose the ability to enforce consistent policy and you lose visibility into what is leaving the network. Chokepoints also make it harder for attackers to hide, because they can't easily route around controls. A core design lesson is that convenience often creates many paths, while security tries to create fewer, more controlled paths. That trade-off is the heart of chokepoint thinking. Now let's connect chokepoints to why they help resist intrusion specifically. Attackers thrive in environments where they can blend into normal traffic, and normal traffic is harder to define when everything is allowed. When outbound traffic is filtered through a controlled point, you can apply consistent rules, such as blocking known risky categories, restricting uncommon protocols, or requiring certain types of authentication for access. You can also collect consistent logs that allow defenders to see patterns, like a sudden spike in outbound connections or repeated attempts to reach unusual destinations. Even if you don't block an attacker immediately, chokepoints slow them down and reduce stealth. They also force attackers to use the same constrained paths that legitimate traffic uses, which makes their activity more observable. In security, slowing down an attacker can be just as important as blocking them, because it buys time for detection and response. Lateral movement barriers are the internal counterpart to egress control, and they are just as important. Lateral movement means an attacker moving from one internal system to another after they gain an initial foothold. This is often how small compromises become major incidents. because the attacker uses one compromised workstation to reach servers, then uses those servers to reach even more sensitive systems. If the internal network is flat, lateral movement can be fast and quiet because many devices can talk to each other by default. Barriers to lateral movement are created through segmentation, access control, and careful limitation of which systems can communicate. The idea is not to prevent all internal communication, but to prevent broad, unnecessary communication that gives attackers too many options. When internal pathways are constrained, attackers need more steps, more privileges, and more time to reach high-value targets. A beginner-friendly example is to compare two scenarios. In one, every workstation can directly talk to every server on many ports, and in the other, workstations can only talk to a small set of application servers on specific ports. In the first scenario, a compromised workstation can probe servers freely, try credentials, and look for weaknesses without much resistance. In the second scenario, the compromised workstation has fewer targets and fewer allowed pathways, so many probing attempts are blocked immediately. This not only reduces risk, it creates clearer signals for monitoring, because blocked access attempts stand out at the boundary. Another effect is that defenders can apply stronger authentication and logging on the few systems that are reachable, rather than trying to defend an enormous open landscape. Lateral movement barriers turn a large, fuzzy interior into smaller, manageable compartments. One important design pattern is to separate user networks from server networks and then further separate servers by function and sensitivity. A database server should not be reachable directly from a user workstation unless there is a very specific, justified reason. Instead, the database should be reachable from an application server that mediates access and enforces business logic. That mediation reduces exposure because it limits who can speak directly to the most valuable systems. It also limits what kinds of traffic the database sees, which can reduce exploitation opportunities. Another pattern is to isolate management interfaces in a separate management network, so administrative access requires passing through controlled entry points. This reduces the chance that a compromise of a normal user device gives an attacker immediate access to administrative controls. These patterns are not about complexity for its own sake. They are about narrowing pathways around the most dangerous targets. It's also crucial to recognize that internal trust often becomes the weakest link, especially when people assume that if something is inside, it must be safe. Many attacks succeed because internal systems accept connections without strong authentication or because they rely on the idea that only legitimate users are inside the network. Modern security assumes that internal compromise is possible, so internal access should still be treated with caution. That means enforcing authentication, limiting privileges, and monitoring internal traffic at key seams. When you combine that with segmentation, you create internal barriers that force attackers to repeatedly prove access as they move. Each time they have to prove access, they create opportunities for detection and denial. This is the heart of intrusion resistance by design. Make the attacker earn every step rather than letting them glide. Egress control and lateral movement barriers work best when they are paired with good identity and device hygiene, because many attackers move using stolen credentials. If outbound access is restricted but stolen credentials can still be used to reach internal systems broadly, an attacker may still do plenty of damage without exfiltrating much data at first. Similarly, if internal segmentation is strong but outbound access is wide open, malware can still communicate and pull tools, making the attacker more capable. That is why defenders aim for layered constraints. Constrain outbound paths, constrain internal paths, and make privileged access pathways narrow and well-monitored. Even at a beginner level, you can see the logic. You want to reduce both the attacker's ability to communicate outward and their ability to expand inward. The combination makes the environment less forgiving to attackers and more manageable for defenders. Another important idea is that controls should be designed so normal business use is still practical, because unusable controls get bypassed. If users cannot do their jobs due to overly strict outbound restrictions, they will find workarounds, and those workarounds can become hidden exposure. If internal segmentation breaks critical workflows, teams will request broad exceptions, and those exceptions can erode the barriers you built. A monitoring-ready approach helps here. because you can observe which connections are truly necessary and then build rules that reflect reality. You can also roll changes gradually, tightening where you have confidence and learning where you need adjustments. In security design, success often looks like fewer broad allowances and more precise allowances, maintained over time. The key is to treat the network as a living system that needs governance, not a one-time diagram. As we close, remember the simple objective behind all three concepts. Control pathways so an attacker cannot easily hide, communicate, or spread. Egress control limits and monitors outbound traffic so compromised systems cannot freely reach command servers or send data out. Chokepoints concentrate enforcement and logging so policy is consistent and suspicious patterns are visible. Lateral movement barriers constrain internal communication so an initial compromise does not automatically lead to access everywhere else. Together, these design choices shift security from reacting to intrusions to shaping how intrusions can unfold. If you can build a network where attackers are forced into narrow, observable corridors, you make detection easier, response faster, and damage smaller. That is what it means to resist intrusion by design, even when prevention at the outer edge is not perfect.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.